Okay, so sorry about the delay. The good thing about giving the very last talk of the conference is that a lot of concepts have been explained in the earlier talks. For instance, today I will be talking about a lot of things that you guys, since I've been sitting there for the whole day, I've been a lot of things that you guys are doing. For instance, proximity, a two-dimensional Rorschach system to a magnet, and as well as putting, for instance, a superconductor or some metallic materials on top of a topological insulator. But the basic scheme that I will be explaining about is, let's say, some effects by breaking the spin momentum locking. And actually, by breaking, to be more precise, what I mean by breaking is more like disturbing the spin momentum locking by means of proximity to a magnetization. And I would like to predict a bunch of novel effects that, as far as I know, haven't been predicted yet. And this work is done with my student, Antonio Zegara in PUC in Rio de Janeiro, and also as well with Carlos Egues, the organizer of this conference, as well as Manfred Sigris in ETH. So let's see, how does this work? Okay, then I will just use the main power. Then, today I will be focusing on two different kinds of systems that have spin momentum locking. The first one is the usual two-deck that has Rorschach spin orbit coupling. And I will mention this well-known Edelstein effect, as well as the new phenomenon that we predict when you couple it to a ferromagnet, namely the existence of a persistent current. And then I will switch gear to three-dimensional topological insulators to be more precise, the surface state of it. And first, I will discuss the linear, the pristine case when it is, just let's say isolated in the vacuum, and the Edelstein effect here. And then later, I will discuss the situation when you put a ferromagnet on top of it, and how the spin torque is generated, and as well as the appearance of a spin of a persistent current. Now, this is quite a hot topic because there's topological spintronics stuff that is going on. Yeah, okay. How should I hold this thing? Now it's on? Oh, yeah. Okay, much better. So, in terms of the two-deck part, I think everybody is quite familiar with it here. That if you just have a simple parabolic band and coupled to the Rorschach spin orbit coupling, the spin eigenvalues for these two bands form this kind of helicity. Let's say the outside is counterclockwise and the inside band is clockwise. And one very direct consequence of this is the so-called Edelstein effect. Namely, if you apply the electric field in a semi-classical picture, is that these two framing surfaces will be shifted towards or in the opposite direction of the electric field. And as a result, you will generate a spin accumulation because, here on this side, the spin is polarized in Y, while on the other side is polarized in minus Y. And because of the shift of the electric field, this side will be more populated than the other side. So you will naturally generate spin accumulation that is polarized in the Y direction. Now, but once you couple a magnetization to it, for instance, you deposit this 2D material on top of some ferromagnet, then it is known that the spin momentum locking will be disturbed. Well, this is what I mean by breaking, but it's actually disturbed. And for this part of the talk, I will focus particularly on the situation where the magnetization is polarized along Y direction. Now in this case, the spin momentum locking will look something like this. You see, the simple argument is that because this side of the spin is pointing along positive Y, and the other side is along negative Y, so this side will become more energetically favored, And therefore, the whole thing, this outside band will be shifted toward the positive direction, but inside band will be shifted towards the negative one because of a simple argument. And the whole spin helicity will be slightly distorted. And not only the Fermi surface is doing this, the entire band is actually doing the same thing, yeah, because of this shifting argument. Now, based on this, we came up with this idea. Does it mean that, okay, obviously, now this band structure is asymmetric between positive x and negative x direction? Would it mean that your the entire Fermi sea is carrying a finite momentum, and hence your system will produce a current? Now the answer is actually no, because you can go ahead and calculate the expectation value of the current operator of the eigenstates, which according to the Feynman theorem, this is nothing but the group velocity of these two bands. Now you can go ahead and integrate this group velocity over the entire Fermi sea. Then you see that the result is obviously 0, because this is nothing but the derivative of the bands. And then you integrate it over the entire Fermi sea, right? So you integrate from the derivative of this function from here to here. But this function here and here have the same value, so they cancel out to be 0. So in other words, a symmetric, or I should say a symmetric band structure does not necessarily imply a spontaneous current that is generated in the system. However, this situation is quite different if you open up a boundary in your two-dimensional system. Let's say instead of considering infinite two-dimensional electron gas, I consider the case that in the x direction is continuous, but y direction is open. In other words, it's a ribbon kind of geometry. In this case, we try to solve the same problem on the lattice. Let's say here I have the usual parabolic part, and here I have the Rashba part, which you can also build a hopping to describe it. And here is the magnetization pointing along y direction. As a result, you see that the band structure becomes like this. Now, in the x direction, I have still the momentum is quantum number, but the y direction it is not, because essentially in this case, you are taking this two-dimensional dispersion, and then you cut it into slices, and then you collect them all together along x direction, and then you see that the band structure looks like this. And once again, the asymmetry between positive kx and negative kx is pretty evident. Now the interesting thing is we go ahead and calculate the local current that is coming out of this open boundary geometry, and we found that it turns out that the current is actually not 0. Well, the total current is 0, but locally it is not. So you can build a current operator out of this lattice model, and then you just take the expectation value of your local of your energy eigenstates, and then times the Fermi function. Then the physical picture is that the system will form this kind of what we call the laminar edge current, in the sense that you have sort of a counter-flowing positive and negative currents that are equal amount and flowing in the opposite direction. Now we show this by diagonalize this whole lattice in some strip geometry with a finite width. For instance, this is the current that is flowing in the x direction plotted as a function of the transverse coordinate y here. And here I'm showing you the simulation in a strip of 20 sites width. And you show that there's some positive and negative currents non-zero. And then you can go ahead and calculate a wider strip, let's say from 20 sites to 40 sites. And then you start to see that these patterns are actually localized at the edge. You have positive and negative currents that they are localized at the edge. And you go for a wider one, for instance, 60 sites width ribbon. And you still see that some laminar currents that are localizing at the edge. Now, and we have checked that it's not a numerical error, and at larger and larger system size, this pattern of this laminar current, they saturate. And this is, and moreover, this is a contribution coming from the entire asymmetric band structure, yeah? And moreover, this whole current is summed to be 0. So this is consistent with the Feynman theorem that I was telling you. In other words, globally you have no current, but locally you have this laminar flow of positive and negative current. So this is what I would like to, the information I would like to convey. Now, what is even more interesting is that, experimentally it's very hard to make this kind of closed ribbon geometry, right? And usually in the transport measurements, what experimentalists do is they build a whole bar and then you can build, all your contacts and so on. So we can also study this lattice model in this entirely open, isolated sheet geometry and plot what the local current looks like. And here I show you the simulation. Here the red color is the current flowing in the positive direction, and blue is current flowing in the left. Now the entire sheet is isolated, and the magnetization is pointing in the y direction. So in summary, the result seems to suggest that in this kind of open sheet geometry, you still will have a current. And the current will form some kind of network of currents. And the network of current is such that the local current is non-zero, but locally the continuity equation is satisfied. In other words, at every lattice site, the current flowing in is equal to current flowing out. So the entire pattern is stabilized. But nevertheless, close to the edge, you still see that there's this kind of counter-flowing laminar flows. And then at the edge, they just die out here. Yeah. And moreover, because this kind of current is an equilibrium current, and it's essentially the zeroth order in the Boltzmann equation. Yeah. And because of this, it's actually very stable against whatever perturbation you wanted to put. For instance, here we have tried that what if the magnetization is not uniform? We can put some magnetic domains, and then this is realistic issues, right? And moreover, we can also put in impurities shown in these white dots. And you see that the current pattern will be greatly deformed, but nevertheless, the currents are still there. Yeah. And moreover, at every cross section, we can sum over the current flowing in the positive and flowing in the negative direction, as I'm showing you here. You always have equal amount of positive current and negative current flowing against each other, whichever position you are. Yeah. So so this is the first part of my talk. The prediction is you have this kind of counter-flowing current, and how do you measure it? Well, we have some ideas, but let's say this is still work in progress. Because this is gonna be quite hard to measure, because we recently concluded that this laminar flow is likely not going to show up in any transport measurements, because this is an equilibrium current. This is kind of like the equilibrium part of the quantum Hall effect. But nevertheless, maybe you can try to measure the field that is generated by these currents. But you see that, well, these currents are counter-flowing, so the current cancels out in a very small scale. So it seems like very difficult to measure the field as well. So yeah, let's just say we are still thinking about it. Now, the next part of my talk, I will switch gear to talk about topological insulators. And first, I would like to discuss some spintronic effect of an isolated topological insulator of some properties which I think no one was pointing out before. Now, again, this we have heard a lot of talks in this conference that we can just focus on this surface state Dirac cone, which are responsible for these spintronic effects. Now, you will also have Edelstein effects if you apply electric field or electric current. And now the simple physical picture is that you know that the spin momentum locking of this Dirac cone for the electron cone and for the hole cone are actually opposite. Now, once you apply an electric field, the electron cone is going to be shifted in the positive direction, and the hole cone is going to be shifted to the negative direction. But the spin polarization along the direction that is shifted is the same, and therefore you will produce a net spin accumulation instead of canceling out, just because the helicity of these two are actually the opposite. Yeah. And then it has also been worked out early in the 2010 that the effective Hamiltonian of this surface state looks just like the Rashba spin orbit coupling, except we don't have the parabolic part. Now, starting from this, I would like to do a more rigorous calculation of the Edelstein effect. And moreover, I would like to emphasize that the Edelstein effect here is actually quite different from the usual Edelstein effects in the 2DEX or in any metallic thin films. For a simple reason that the density of state is linear near the Dirac cone. Yeah, and this is also, of course, well known in graphene since they studied the transport in the early days. Now, because of this linearity, if you consider random impurity scattering in these surface states and use a simple Fermi golden rule calculation, you actually will see that the scattering rate at the surface of these topological insulators, they are actually proportional to the density of states. In other words, the mean free time of electrons are actually vanishingly long as you are closer to the Dirac point. And once again, this is also well known in the graphene business, and people use it to study the transport properties and so on. But if you and there are also these pioneering works by Burkhoff et al. And Ajogar et al. That considered this strictly for the surface state of topological insulators. Now you put this Fermi golden rule into this Boltzmann equation, and then use a semi-classical way to solve for the spin accumulation as induced by an electric current along y direction. Then you got a very interesting result, namely that the spin accumulation is independent from the chemical potential and also independent from the temperature. Yeah. This is rather surprising because you see everything here that appears is just proportional to the field. It's independent from temperature, and also chemical potential does not appear. In other words, it will be independent from where you cut, where your chemical potential is located. In the hole cone or in the electron cone, doesn't really matter. You get a constant. Yes?
Just wait a second, please.
It's just a quick comment. So the calculation you are showing is performed at the level of the first Born approximation. So then you find that the transport time, your tau, is basically 1 over the energy, because the density of states is energy.
Yes.
But in graphene, actually, when you have resonant impurities or short range disorder in general, you have to do the calculation at the T matrix level because the Born series is no longer valid. And then you find a different relation. Basically, you find that the transport time now is proportional to the energy.
Yes.
In such case, then this interesting formula that you are showing for the current-induced magnetization would change and then would depend on the Fermi energy.
Oh, I see.
So what I'm saying is that this particular result is just a coincidence because you are doing the calculation at the Born level, which in graphene happens to tends not to be valid. So unless you have very specific type of disorder. So for realistic disorder, you'll have to do the calculation at T matrix, like then it's
right. So this is really a very simple-minded semi-classical Boltzmann calculation, as you mentioned it out. But we can discuss it a bit later about this. Now, and the only thing that is left that determines that what's the magnitude of this spin accumulation is specific strength of the electric field is just what this factor that I call the cleanliness of the system. Essentially, it is just the impurity potential square multiplied by the strength of the, multiplied by the density of the impurities. Yeah, and if this 1 over gamma is, the larger it is, the cleaner it is, and then you have more field-induced spin accumulation. Now, but what I mean to say is that this simple-minded calculation seems to be agreed pretty well with experiments. For instance, in this Denkart et al. Experiment, they measure the temperature dependence of this field-induced spin accumulation, and they, as shown here in the red dots, they seem to be pretty temperature independent. And secondly, you know that at the surface of topological insulators, there are actually a lot of realistic issues. For instance, in this paper by Nagaosa group, they actually pointed out that you have this kind of surface band bending, so the chemical potential near the surface is actually not exactly, the values inside the bulk. And moreover, this STM results in Yazdani's group shows that at the surface, you actually have this kind of hole-rich puddles and also electron-rich puddles. In other words, the chemical potentials are actually not locally, are actually varying locally. Yeah. So what I'm saying is, despite all these results, the fact that you still observed spin, field-induced spin accumulation seems to be quite, seems to agree pretty well with this result that I'm showing you with a simple semi-classical calculation, namely because this mean free time is basically linear to energy. Okay, now coming to the very last subject of my talk, namely now we have a nice spin momentum locking in this in this surface state of topological insulator, right? So now let's try to break it by coupling, let's say by depositing a ferromagnetic metallic thin film on top of it. Now this this particular system becomes, let's say, highly pursued recently because they found the current-induced spin torque in this particular system. And moreover, the experimental result seems to suggest that the efficiency of this spin torque, this magnetization switching, can be comparable or even larger than this prototype, let's say, cobalt platinum systems. So this seems to be very exciting because it seems to be like this kind of topological spintronics can be it can even compete with the usual heavy metal spintronics. However, in this particular system, I would like to mention that if you just think for 1 second, you will immediately think that this is actually a very puzzling result, because you put a magnet on top of a time reversal invariant system. Then, first of all, how do you know that the edge state even survives? How do you know that the surface state even survives? Yeah. And moreover, even if it survives, to what extent will it be modified? Now, this is the question that I would intend to address. And moreover, you know, in this conference, you also hear a lot of people addressing this spin torque issue. You know, this metallic ferromagnet itself can already generate spin torque. And how do you know that it is not you know, it's just the fact that you put this magnetic thin film itself that is doing the job. So to answer these questions, the status of this and also the contribution of this surface state, we study, let's say, a simplified model. We study a simplified 2D model. In other words, this 2D quantum spin Hall effect, but side by side in a planar junction with a ferromagnetic metal. So this is like a 2D version of this 3D setup. And yeah, so at this level, let's say this is more like a theoretical model. But nevertheless, we think that the results that we review in this simple model has some, we can learn something to this kind of real 3D situation. Now, we built a lattice model to study this, because it turns out that if you really want to correctly capture the status, how the edge state do in this kind of metallic and topological insulator junction, it seems like this kind of lattice model is the only way to study this. Because if you just think for a second, this is another very puzzling question, because essentially you are putting a Dirac model right next to a Schrödinger model, yeah, which is the first order differential equation to a second order differential equation. And you put them together and ask if the edge state still survives. So it turns out that we think probably this to solve it analytically from this kind of Schrödinger versus Dirac equation phenomenology is probably not really a right way to go. So we decided to build a lattice model to study this. And the first thing that I would like to mention is that it seems like not so many people have actually mentioned this. You know, although we call it topological insulators, but from energetical point of view, it is more like a semiconductor, because you know the band gap is only 300 milli-electron volt, right? Now you put a semiconductor with a ferromagnetic metal or any metallic compound. It has been known since the, I think, 50s or 60s This is the so-called Shocking-Mott rule for this metal semiconductor junction. So when you put a semiconductor with a metal together, the chemical potential of each of them will have to be shifted in order to, will have to be shifted at the interface. And the reason is that you have to align the work function of these two materials in order for them to make contact to each other. As a result, we think that generically you could have two different kinds of situations. In this kind of a 2D quantum spin Hall effect versus ferromagnetic side junction, the energy bands actually looks like this. You have the topological insulator band. This is the conduction band. This is the valence band of it. And in the middle, this cosine light band is the bands from the ferromagnet. Now you can imagine you just put them side by side, and then you gradually turn on the coupling between them. And then now you have this Dirac cone as shown in the middle. Now if I zoom in, and the system will look like this. You have this ferromagnetic bands, and you have the topological insulator bands. This is a situation that we call it the pristine situation. Namely, that the Dirac cone actually survives the coupling to the ferromagnet, because you see that this entire cone is actually outside of the ferromagnetic band. But we think that in principle, generically, you can have the second situation that because of the Shocking-Mott rule and because of the shifting of the chemical potential, that this Dirac cone is completely submerged into this ferromagnetic bands. And if this situation happens, then you don't have any Dirac cones anymore. You can't even identify it anymore. Just, all the bands are all meshed up together. Yeah. So at least in this simple model, we can study both situations. This is just simple tuning of the relative chemical potential between the two materials. For now, let's focus on this pristine situation that I was showing you. At least here, you can still point it out, identify by hand that, look, this is still my Dirac cone, and this is still my edge state. So the edge state still survives in this kind of topological insulator and ferromagnetic metal junction. Nevertheless, what is interesting is if you actually look at the wave function of the state that you identify at the Dirac cone, you actually see that the edge state percolates into the ferromagnet. Now here, what I'm plotting is the wave function of this edge state, and here's long x and this is long y. So on this side, you have the two-dimensional topological insulator, and the other side is the ferromagnet. So on this side, you see that it's exponentially localized as the usual edge state. But on the other side, you also see that there's a small leakage inside the ferromagnet. So in other words, the edge state is not entirely localized inside the topological insulator. Now, this is the case when the interface is weakly coupled. If you have a stronger coupling between the two materials, then you start to see that this edge state wave function is gradually diminished, and the weight inside this ferromagnet becomes more. Yeah. So you can have this kind of what we call percolated edge state. The relative portion between that this Dirac cone wave function is inside the topological insulator and is inside the ferromagnet actually depends on how strong they are coupled. Okay, so the situation is much more complicated than you think. This is what we learned from this. And also another thing that I would like to mention is that if you look closely to this energy dispersion here, you will actually find that the energy dispersion is once again asymmetric between positive kx and negative kx, although they look very similar. But if you look closely, they are actually different. For instance, this bulb is a bit larger than this bulb, and this is a bit larger than this as well. And because of this, according to my argument before in the 2 deck, it seems like I can actually produce a laminar persistent current, as we have calculated here as well, that you just diagonalize your lattice and sum over the eigenstates, the current operator of it. And then you see that, once again, you have this kind of laminar current that's localized near the edge. Let's say in topological insulator, it's positive, but in ferromagnet, it could be negative and positive. And the total current summing up together gives 0, once again, because it has to satisfy the Feynman theorem. But locally, it could be not 0, and it forms this kind of laminar flow. And finally, we would like to answer the issue is, does the edge state contribute the most to a spin torque? We can also analyze this using a simple linear response theory, because essentially we are just calculating the spin accumulation as induced by electric field. So we can do this by a simple linear response theory, and the lattice version looks like this. You just take a current operator, take a spin operator, and then times this Fermi factor. And we can calculate for the submerged case or for the pristine case, and then you can calculate this response function susceptibility in front of it. Now, how do we know that does the edge state contribute more or the ferromagnetic state contribute more to this susceptibility? Or we can also do this. We just look at this response function. This is summation over all the eigenstates in your spectrum, right? And then we just ask which eigenstates contribute the most to this response. And then we look at the wave function of this state that contributes the most. Then we say that if this state that contributes the most, that has a wave function profile looks like this, then I know that this is the edge state. If the wave function profile looks rather like this, it has oscillating behavior in both x and y direction, then I know that this is a state contributing from the ferromagnet. And using this logic, and plus, we have both the pristine case and we have the submerged case, and you can have magnetization pointing along x, along y, and along z, and then considering all these possibilities together, we conclude that in the pristine case where the Dirac cone survives the ferromagnetic bands, the field light torque is actually coming from the edge state, while the damping light torque is mainly attributed to the ferromagnetic light state. Well, for the submerged case where the Dirac cone is no more, actually, as you expected, you can't even identify the edge state anymore, and actually all the wave functions that contribute the most to this response function is more ferromagnetic states. Now this brings me to the end of my talk. And first is a prediction that in the two-dimensional metallic systems that have Rashba interactions, that this kind of in-plane magnetization can give you a persistent current. And then secondly, under the influence of impurities, the Edelstein effect of the surface Dirac cone will give you the Edelstein effect of the surface state is actually constant of chemical potential and, and temperature. And then finally, in this kind of topological insulator and ferromagnetic metal junction, the existence of edge state actually depends on a lot of things. Yeah? And also, shall the edge state exist, it will percolate into a ferromagnet. And does the edge state contribute the most to the torque? It also depends. And also, there's prediction of persistent current there. And thank you for your attention.
So, questions? Thanks for this very interesting talk. So I think you might have said it, but I missed it. What's the condition so that the ferromagnetic bands do not cover the bands from the edge states?
So you can, okay, at least from a